Thank you very much. It's a real pleasure to be here, and please feel free to interrupt me. Jeanette has asked me to make a recording of this, but it's going to be a very informal recording. So if you're watching the recording, don't expect anything professional here. It's just something I'm doing on my laptop, and I will edit out any questions from the audience before I post it anywhere. So don't worry about that aspect of it. So I'd like to talk about this pretty interesting result that came out of a bunch of work that we were doing in my group. It's very much a collaborative work, and these are the key people who have contributed in a big way. The primary references for this work are two archive papers. A little bit of the background. The work came about first from trying to understand in a little more detail a theorem that is called the CAP theorem. That's really a pretty incredibly obvious result, and that one that in a way doesn't even really rise to the level of deserving a name because it's so obvious, but nevertheless it's an interesting result that has kind of changed the way people think about database systems in a pretty significant way. So this was introduced first by Eric Brewer more than 20 years ago in the year 2000, okay? And what he said was very simple, which is that in a distributed database system, so in distributed database systems, you have replicated data. So the data gets copied into multiple machines, typically around the world. And you are able to access records and update records in this distributed fashion. And one of the big challenges in designing a database like that is to maintain consistency, which is an assurance that whenever someone accesses a record, that there will be, in some sense, an agreement about what the value of the record is across the whole database, even though the copies are replicated and the data is being updated. There's more local versions of this problem. For example, if you're familiar in computer architecture with the cache consistency problem, that's a very closely related problem on a much smaller scale. Okay, so this problem of maintaining consistency is important in a lot of systems. Availability is simply the ability to access the data that you're trying to maintain consistency on. Okay, and one of the challenges is that brute force techniques for maintaining consistency will be very expensive and will make availability, they'll compromise availability. So for example, if you store all your data in a centralized server, well, first of all, then you have a single point of failure, but you're also, every node then is vulnerable to network degradations. And so availability may be lost due to network degradations. And so Eric's observation was simply that when your network breaks, which he called network partitions, you have to give up one of consistency or availability. You can't maintain both, okay? So that's obvious, right? You've got replicated data. If your network breaks and you get a request for the value of a record, you can either tell the requester what you know, or you can wait until you're sure that what you know is the consistent value and only then tell the requester what you know. But if you've lost network connectivity, you lose the ability to do that consensus, right? So you have to give up one of either availability or consistency if your network breaks. So the short story that I'm going to tell you now is that we have quantified all three of these quantities. We don't think in terms of the network breaking completely, but instead we think of networks as having delays. And a broken network is just a network with very long delays, okay? But all networks have delays. And every amount of delay will force you to do some sort of compromise between consistency and availability. No matter how small your delay is, there's going to be a trade-off between consistency and availability. And we've quantified both of these, consistency and availability, so you can measure them. And moreover, we have developed a programming framework in which you can design programs that are very explicit about the trade-off. They can specify exactly what the availability requirements are. They can specify what the consistency requirements are, and you can derive from that the requirements on your network. Or you can start with what your network gives you and then derive what the possible consistency and availability numbers are that you can achieve with that network. Okay, so that's the big picture, and that's the story that I want to lay out for you. But a little bit more than that, I'd also like to apply this to cyber-physical systems and not just databases. In fact, I've become convinced that this result is fundamental to any distributed system, and that almost all systems are distributed to some extent at least. And consequently, the applicability of this result, I think, is enormous. I think it applies to almost any interesting engineered system. Okay, so let's look at it very specifically. So if you've got two software components connected by a network, and they each maintain a copy of a shared variable X, okay? Then, as I said, consistency is simply agreement on the value of the shared variable. And in databases and in a lot of applications, this is considered an ingredient in trustworthiness, right? And availability is simply the ability to respond to reads to this variable. So you have a user wants to know the value of the variable. How quickly can you give them the value of the variable? In the context of cyber-physical systems, we extend the notion of consistency to agreement about the state of the world. So if you have software components that are distributed that both have sensors that are reading the value of the world, okay, agreement on some notion of what is the current state of the world is this extended form of consistency, right? And similarly, availability becomes the ability to respond to reads and writes. So in this case, reads and writes are sensor and actuator actions, and consequently, availability is simply another word for the sensor to actuator latency, which is a very important ingredient in any control system design. Okay, if availability degrades, that latency increases. And the question is, how can you get that latency down to improve your control system design? And one of the things I'll show you is that you can sacrifice some consistency to improve availability and thereby improve your control system design. Okay, so let's look at two examples from a very intuitive perspective first, and then I'll get a lot more rigorous. Okay, so this is a purely intuitive description of two examples, and I use these examples to point out that whether you want to emphasize availability or consistency is completely application dependent. There's no hard and fast rule that you should always make things consistent. No. And there's no hard and fast rule that you should always make things available. That's simply false. It very much depends on your application. So here's an application, okay? So this is an ADAS system, advanced driver assistance system, that has a forward-looking camera that identifies pedestrians. This is a mock-up of a pedestrian at a trial that Denso did. And you've got a camera looking forward, and then some vision algorithm, okay? A lot of the car manufacturers are experimenting with designs where the vision algorithm gets done in the cloud, which scares the heck out of me, but they really are doing that, okay? So this could be getting done in the cloud. And then it's determining whether or not there's a pedestrian there, and then applying a signal to the braking mechanism, the braking subsystem, to apply the brakes. But in this particular example, you also have a brake pedal in the car, and that's got a sensor that can also apply a stimulus to the braking system. So now the question is, should this system emphasize consistency or availability? Well, let's look at exactly what that means, okay? So the camera takes a snapshot of the state of the world at some time t. And then you do some analysis of that image that has been created to determine whether there's a pedestrian. And the result of that analysis is information about the state of the world at that same time t, right? Similarly, the brake pedal experiences the driver pushing on the brake, for example, at some time, say, t plus epsilon, a little bit beyond t. okay? So should the brake system here wait until it's got the information about the state of the world at time t before it proceeds to process information about the state of the world at time t plus epsilon? Okay? If it waits, that's a requirement on consistency. Okay? If it doesn't wait, that's a requirement on availability. So you can see that in this case, because we know that this is a braking system, the answer is really obvious, right? If the driver pushes the brake pedal, you want to respond as quickly as you can, regardless of whether you've heard from the cloud about whether there's a pedestrian in your field of view, right? A software system doesn't know that semantics, okay? So a software system couldn't possibly know that, yes, you really want to go ahead and process this event, even though it is logically in the future compared to the event that you still haven't seen, okay? So another way to think about it is that you want the braking system in this case to process information about the physical world out of order, because you want it to be highly available, particularly to this pressing of the brake pedal. Okay, so in this particular example, you want to emphasize availability over consistency. Let's look at another automotive application. This is a four-way intersection. By the way, the programs that I'm showing are programs written in this programming framework that I'm going to describe later in the talk called Lingua Franca. Okay, so in this particular case, it's using an open source automotive simulator called Carla that generates these nice videos of what's going on. But you've got, so in this case, in this test case, we've got 4 vehicles approaching a 4-way intersection, and a roadside unit that's mediating access to that intersection. And now the question is, in this system, do we want to emphasize consistency or availability? So in this case, consistency would be agreement on the state of the intersection, and availability would be the ability to enter the intersection. So what do you think? Do we want to emphasize consistency or availability here? Consistency, obviously, right? You want every car to agree on the state of the intersection before any car enters the intersection, and you'd rather have all the cars stop and not enter the intersection, losing availability, rather than have them enter the intersection on the basis of inconsistent data. Okay, so I've given you 2 examples here that show that it's completely application dependent, and there's no software system that can give you a hard and fast rule about whether you should emphasize consistency over availability. You have to do this on an application dependent, in an application dependent way. Okay. Now, the next thing I'd like to do is probably the primary reason why this paper has gotten rejected several times. Consistency is actually a pretty hard to understand concept. Okay, because naively, it's agreement about the state of some distributed subsystem. But what do we mean by agreement? And what do we mean by state? Okay, you could naively say, well, okay, the system has some state, and agreement is that at an instant in time, everyone agrees on what the value of that state is. But there is no such thing as an instant of time in a distributed system. I mean, you don't have access to it in practice because we don't have perfect clocks. But even in theory, we don't have access to it. Okay? In fact, if you dive into the fundamental physics, the whole notion of a state of a system that occupies space is suspect. Okay? Let me show that to you in a very hopefully clear way. So suppose you have 2 physically separated state machines. This is, by the way, if you're interested in diving into this article more, into this idea more, I have elaborated a discussion of this in a paper called Determinism, published in 2021. But okay, you've got 2 physically separated state machines, and at some point, the state machine on the left transitions from state A to state B, and very close in time to that, the state machine on the right transitions from C to D. So now, what is the sequence of states that the whole system goes through? Okay. It's going to go from the state AC, which is the pair of initial states, and it's going to end up in the state BD. Okay. But it could do that directly by simultaneously taking these transitions, or the transition on the left might occur first, and then the transition on the right, or vice versa. The transition on the right might occur first, or the transition on the left might occur first. In a distributed system, there is no ground truth. If these two state transitions occur sufficiently close in time, okay, then one observer will see the system go through this trajectory, and another observer will see the system go through this trajectory. And both of those observers are seeing truly the state transition in their own frame of reference. So in different frames of reference, you get different state transitions. And so the intermediate states and the state that the system is in at any instant in time is actually not well defined. All right. It turns out, and I'm not going to go into it here, but Bell's theorem, which is a theorem in quantum mechanics, also undermines the notion that the state of a system is a foundational concept. It actually shows that it's a flawed concept. And so fundamentally in physics, you can't really ask what the state of a system is at an instant in time. And anyone who's built a distributed software system knows full well that you can't do it in practice either. Okay. There's no way to ask a distributed system what its state is at an instant in time. So it's not clear that it makes sense to build a whole concept of consistency around something that actually is foundationally flawed, right? So how can we have agreement on something that's fundamentally ill-defined? So let's look at a really practical example. So this is a database example, but applied to a real-world problem. So you've got a distributed database maintaining Joe's bank balance, and it starts at $50, and a deposit occurs in London at 10 a.m. GMT, okay? And a withdrawal occurs in Singapore at 10 a.m. GMT plus 10 milliseconds. So what is the sequence of state transitions for that balance? You're going to have a shared variable, right, across this distributed system. It's going to go through a sequence of values. And if we want consistency, we're going to want that sequence of values to be the same everywhere in the system. Should it be based on these times? Well, the problem here is that at the speed of light, Singapore and London are 33 milliseconds apart. And that means that even with perfect clock synchronization, two events that are 10 milliseconds apart are outside the light cone of each other. And consequently, the order in which these events occur is different in different frames of reference. There is no ground truth to what order these occurred in. Okay, by the way, just as a complete aside, I asked DALL-E 2, the image synthesizer from OpenAI, to generate an image of a globe that included both Singapore and London. And this is what it came up with. It invented a new place that is somehow a combination of the names Singapore and London, which blew my mind. But anyway, that has nothing to do with the core argument here. Okay, so what should we do, right? I mean, a bank is going to want to know whether they should charge Joe for an overdraft here, right? Did an overdraft occur or did it not? Okay, that's a key question and it matters. All right, so what should a bank do? Well, in practice, what a bank does is really pretty straightforward and pretty useful. When the deposit occurs in London, it's given a timestamp drawn from a local clock. Okay, just a local clock. You got a clock there. Use it, give it a timestamp. That's a number. In Singapore, you also have this withdrawal. You give it a timestamp, again, based on a local clock. All right, now you have two timestamps. Those are two numbers. Those two numbers have a well-defined order. Okay? They're numbers. Of course they have a well-defined order. So now you define the semantics of the database is that transactions occur in timestamp order. And now your challenge is simply to build a software system that ensures that every observer that sees both of these events sees them in timestamp order. Okay? Now, I don't want to suggest that that's a simple software design problem. It's far from it. It's not a simple software design problem, but it's a well-understood software design problem. You have a few experts. We have a few experts in the room who know how to do this, right? Distributed discrete event systems have been around since the 1970s, and there's a rich set of very sophisticated techniques for building distributed systems where every component is guaranteed to handle things in timestamp order, okay, even across a distributed system. So you can do that. And in fact, this is done routinely. In fact, probably one of the world's biggest databases, Google Spanner, does exactly this. This is a database that spans the globe. It has replicated data in data centers all over the world. And it uses these timestamps and defines the semantics of every transaction with the database to be simply the timestamp order. Okay. Now, obviously, in order for this to be useful, you want these clocks to be at least somewhat synchronized, right? They don't have to be perfectly synchronized. That's an important thing to notice here. And I'm going to show you, in fact, that you can determine how well they need to be synchronized, because if they're poorly synchronized, you lose availability. Okay. And I'll show you exactly how that relationship works. All right. So the key idea here is that you have to separate this notion of logical time from physical time. Physical time is not just an approximation of logical time. It's a semantic property of your system now. Okay. It's the timestamps, and your system is going to handle things in timestamp order. And to the extent that that notion of logical time relates to physical time, well, that affects the usefulness of your system, but it doesn't affect the correctness. Okay. So in this notion of logical time, every event in the system occurs instantaneously at a logical time t, where t is simply drawn from some totally ordered set. Okay. And what you want your software system to do is ensure that all observers see events in logical time order. Okay. Which is hard to implement, but we know how to do it. So hire an expert. Any two events with the same logical time are logically simultaneous. So this is one thing that you gain with this notion of logical time that we don't really have in physical time. Physical time does not have a clean notion of simultaneous events, but logical time does. The numbers are the same. Okay, so you're going to need to design your system to deal with simultaneous events, right? Is it an overdraft if these two deposits are given the same timestamp, or is it not? That's a business decision. Okay. So for physical plants, nothing really changes, right? But let's look at a situation where perhaps based on sensor data, this software component updates a variable X at some node J and assigns it a timestamp using its local physical clock. And then it notifies another software component. And I'm going to show you that it can be very useful actually to modify the timestamp in this notification. In fact, I'll show you that that's a systematic way to relax consistency requirements. Okay, but you don't have to. You could just preserve the timestamp when you send it, and the other software component gets a notification with a logical time that is greater than or equal to the logical time at the center. So you could increase the logical time, or you could just leave it the same. All right, and I'll show you that leaving it the same is a requirement for strong consistency, and modifying it relaxes consistency and improves availability. Okay, so now I can give you a definition of, in the paper we use inconsistency rather than consistency because it's numerically more convenient. And it's a quantity that's defined in these papers over a whole trace of execution. So we're looking at worst case behaviors. Okay, so over a trace, the inconsistency from node J to node I is the maximum over all events that flow from J to I of the difference between the two logical times. Okay, so perfect consistency is where the logical times are required to be the same at the receiving end as at the sending end, in which case the inconsistency will always be 0. Okay, in fact, it's a constraint that the inconsistency is always greater than or equal to 0, and we simply call it strong consistency if the inconsistency is 0. It's important to realize that now this is a very well-defined quantity in a well-defined system. We now know what agreement means. Okay, what it means to agree is simply that the components all agree on the value of a shared variable at a logical time. And if you require strong consistency, they agree on the value of the shared variable at exactly the same logical time, but you can relax that and allow one of them to lag behind. Okay? So strong consistency is where all nodes agree on the value of a variable at a logical time. And in this case, the value of a variable is simply a function of logical time, not a function of physical time. So the bank balance now becomes a function of logical time, not a function of physical time. Okay. So let's look at how this plays out in the car braking example. So the camera takes a snapshot and assigns it a logical time. And I consistently use lowercase for logical times and uppercase for physical time. So gives it a logical time that it draws from its local physical clock. So now the event has a logical time. The braking assistant is logically instantaneous because it's going to give us information about the state of the world at the time that the camera took the snapshot, right? So we want that time information preserved. So logically instantaneous, even if it's going up to the cloud, doing a bunch of computation, coming back from the cloud. So it takes physical time to do it, but it's logically instantaneous. So the result of that is an event whose logical time is still T1. The brake pedal assigns a timestamp to the press event, and it's a new timestamp based on its own local clock. Okay. And now strong consistency requires the brake component to process those events in timestamp order. So strong consistency in this case, because of that requirement to process events in timestamp order, we can see that that this reduces availability because the braking component can't react to the brake pedal if this timestamp is numerically larger than this one until it knows for sure whether it's going to get a timestamp with a lower value, right? So requiring strong consistency has a cost in availability. Okay, so we can quantify availability as well in a very similar way. So again, we quantify unavailability instead of availability because it's numerically more convenient. So the unavailability at node I is the maximum over all accesses of a shared variable at I of the difference between the logical time of the shared variable and the physical time at which the access occurs. Okay, so in general, you're going to be delayed in your ability to access a shared variable. And so here we have a physical time and we're subtracting from that a logical time. Okay, on the assumption that the logical time represents some measure of when some physical event occurred. And the physical time at which the access occurs is when this variable becomes available. Okay, so this is a pretty natural, intuitive definition of unavailability. And we can see that, again, we have a constraint that this is always greater than or equal to 0, and that perfect availability is where the access can occur immediately. Okay. So there's a third variable that we need to introduce that is due to those software experts that built this distributed system. Okay. In order to ensure that every component processes events in timestamp order, in order for a component to process an input event, you have to be able to guarantee that no other component is going to send it an event with a lesser timestamp. Typically, you have to wait in order to do that. Okay? It's part of how you build such a software system. It's going to take you some time to be able to provide that assurance. We call that time the processing offset, and simply define it to be the difference between the physical time at which you do the update locally and the logical time of that update. Okay? The last quantity that I have to define is one that we call apparent latency. Okay? So apparent latency for a communication from node J to node I is the maximum over all messages that flow from J to I of a difference, again, between a physical time and a logical time. But now this is the logical time of the event at the originating node. Okay, so remember that that is probably relative to the clock at the originating node. It's probably taken from a physical clock at some remote node. Okay, that's a logical time that comes from a remote node. And then this time is the time at which we process the event on this node. I'd like to point out that this is a very easily measured quantity, okay? Because the timestamps can be carried by the messages. And you can ask your local clock what time it is now and just take the difference. And consequently, this latency you can measure anywhere in the system, easily, trivially, right? But what affects this latency? Where does it come from? Well, there's actually 4 ingredients that all affect this latency. One of them is the processing offset. That the more your processing offset, the more your software has to wait to give assurance that things will happen in timestamp order, the more your apparent latency will be. Execution time along the path affects it. So in the case of the ADAS system, whatever vision analysis is being done in the cloud is going to take some time. That's going to affect the apparent latency. The network latency is going to affect the apparent latency. And lastly, the clock synchronization error affects the apparent latency because there's 2 sources of physical time information that come from 2 different clocks. Okay. Notice that all of these quantities, these 3 quantities are all non-negative, but this one can be positive or negative, and it could be quite large. So the apparent latency can even be negative. So you can process events at a physical time that's earlier than their logical time if your clock synchronization is way off. Okay. I'd like to point out that these 3 quantities are very hard to measure. All right. I've gone to conferences where people try to measure clock synchronization error. Okay. It's really difficult to do. You have to put both clocks physically very close together. You have to use a very expensive oscilloscope with temperature controlled probes that are exactly the same length. Okay. And then you've got to put a coil of network cable to pretend that these are actually physically separated. It's really very difficult to measure clock synchronization error. It's also very difficult to measure network latency. One of my most cited papers was written by a grad student of mine who had a really interesting idea for distributed computing, but nobody cites the paper for that. They cite it for the experimental work he did on measuring network latency that he reported in that paper. It's a really difficult thing to do. And execution time it's not that hard to measure. It's very hard to predict, however. So these components are not easily measured, but the sum of them is trivially easy to measure. And the Cal theorem only requires the sum of them. Okay? So the Cal theorem, which is given in these papers, says that the unavailability at node I is the maximum of the processing offsets at node I, or the maximum difference between the apparent latencies from J to I over all possible J other nodes, okay? minus the tolerance for inconsistency. So this theorem follows immediately from the definitions. It's really doesn't really require even a proof. It's just a direct consequence of the definitions. In words, this is what it means, that unavailability is the larger of the local processing offset needed to ensure that timestamps are processed in order. If that number is large, that will dominate your availability. Or the apparent latency minus the tolerance for inconsistency. Okay. So notice that because this tolerance for inconsistency is subtracted out, if you are willing to tolerate more inconsistency, you can improve availability. That's a key part of this message, right? This theorem has a beautiful formulation in a max plus algebra. It's a linear system of equations with a matrix that captures the apparent latencies between any pair of components in the network. So the theorem adapts very well to heterogeneous networks. You can have wired networks combined with wireless networks, combined with super high-speed buses. And you can characterize all of those networks in this matrix and then derive your unavailability requirements as a function of your consistency requirements and so forth. Okay, so a nice theory here. Let's see how to apply it. Okay, so the way to apply it is, the way that I'm going to apply it is using this Lingua Franca language that we have developed. This is a collaborative effort. It's a global effort. There are people, well, mostly in California, Germany, and Korea currently happens to be where the bulk of the people working on this project are. It's a pretty nice programming language, or programming framework, really. It's a coordination language. But one of the features that it has, which was a little bit of a surprise to us, is that you can be very explicit about your availability and consistency requirements in this language. And moreover, you can derive from a program the Cal theorem formulation that relates these quantities. So for example, you can write a program with explicit consistency and availability requirements, and then derive the requirements on your networks from that. You can derive the fact that, well, you know, the availability requirements you've specified, which are specified in terms of deadlines, cannot be met unless your network has latencies less than some amount. And depending on the structure of your program, different connections may require different latencies. And you can completely do that analysis with these Lingua Franca programs. So Lingua Franca is a coordination language. It's not a programming language. It coordinates programs that are written in conventional languages. Currently, it supports C, C++, Python, Rust, and TypeScript. Okay, those 5 are supported. There's beginnings of some support for Lean, which is an interesting language suitable for formal verification, but that's still very early stage. But anyway, the way you write programs in this case is you define reactions in a target language. This looks like C code to me. Yeah, I think it is C code. Whoops. And then you stitch together your components. You specify an interconnection topology that specifies how these things are connected. So for example, this braking assistant system that I have been using as an illustration as a Lingua Franca program. By the way, the diagrams that I'm showing are automatically generated as you write these programs by the Lingua Franca tools. So you don't draw these separately, they're automatically generated. So this connection here says that the vision system is going to send a message to the braking system, and it's going to inject a modification of the timestamp. This is the syntax in Lingua Franca is like this: vision.out connects to braking.in after 10 milliseconds. That says add 10 milliseconds to the timestamp. That's an explicit statement that you can tolerate some inconsistency. You're willing to have this braking system see the state of the world 10 milliseconds off. Okay? Why would you do that? Well, you do that because you gain availability. And in fact, you can show that this relates very nicely to the notion of logical execution time. If the total time that it takes for the vision system to do its work and the network to do its work is less than 10 milliseconds, then your availability here becomes perfect. You can respond instantaneously to the brake pedal without compromising that consistency requirement. Okay? And so now this has become an explicit requirement in the program that you can specify. So the timestamp that arrives here is going to be incremented by 10 milliseconds. And as a consequence, this braking system is able to process events from the brake pedal with logical times that are 10 milliseconds ahead of what it knows it might have been produced from the upstream. Okay? You can go further in Lingua Franca and use what we call a physical connection, which the syntax is like this. You use this squiggly arrow. Okay, if you say vision.out is squiggly arrow connected to braking.in, then what happens is that the timestamp at the originating end isn't even conveyed to the receiving end. And instead, a new timestamp gets assigned at the receiving end using the local physical clock. This is an explicit statement that you don't care about consistency. You have no bound on your consistency tolerance. And consequently, you can assure that the unavailability is always zero in this case. This is sort of satisfying because if you were to design this system without any knowledge of any of this theory, this is probably what you would do. Okay, you would take the input from the vision system when it shows up and use it, and take the information from the brake pedal when it shows up and use it. But one of the downsides of doing that design is that you end up with this unbounded inconsistency and also a non-deterministic program that is much harder to test. Okay, whereas if you put an explicit bound on the consistency, your program remains deterministic, and consequently, you can write regression tests for this program. But that's a trade-off. Okay, so let me emphasize that with this design, with the 10 millisecond specification, if the braking assistant takes no more than 10 milliseconds and the network takes no more than 10 milliseconds, then there's no waiting to process brake pedal inputs. Availability becomes perfect. Okay? But what if your network breaks? Right? The cap theorem. It becomes partitioned. Then the delay over the network is not going to be bounded by 10 milliseconds. So what should you do? Well, now you have a choice. The cap theorem tells us we're going to have to sacrifice consistency or we're going to have to sacrifice availability. We've already sacrificed some consistency, but if the network breaks by more than 10 milliseconds, we're going to have to sacrifice more. Okay? So we have a choice, but we have to make this choice. We either have to sacrifice availability or sacrifice consistency when that network breaks. Turns out that in Lingua Franca, you can specify programs like this that have requirements for correct behavior and then insert fault handlers that either sacrifice availability or sacrifice consistency when your assumptions get violated. Okay? So this is an observation that's really due to this guy, Soroush Bateni, who got his PhD at UT Dallas, then did a brief postdoc in my group and is now working at Apple. But in Lingua Franca, we have two different coordination mechanisms for coordinating distributed software components, one that we call centralized and one that we call decentralized. So the centralized coordinator, if you're familiar with distributed discrete event simulation, it's very much based on the technologies behind distributed discrete event simulation. I know several of you in the room are experts in this. And if you use this coordination mechanism, then when your network breaks, you will sacrifice availability. the program will stop making progress. Okay. If you use decentralized coordination, which is what is used also in Google Spanner, I mentioned Google's global database system, they use something very similar to our decentralized coordinator. If your network breaks, this will sacrifice consistency. So it preserves availability at the expense of consistency. So each component continues to process events even if it loses network connectivity altogether. This technique requires you to synchronize clocks and requires you to put some bound on your assumptions about the clock synchronization error. So the way that this works is that in centralized coordination, if the network breaks and this message just simply isn't getting there, then the runtime infrastructure will block this program and prevent it from doing anything because it can't safely process events in timestamp order. And the choice has been to emphasize consistency. If you can't guarantee that events will be processed in timestamp order, don't do anything. Okay, so that sacrifices availability. On the other hand, with decentralized coordination, the braking system continues operating even if it's not receiving any messages. Okay. It may later receive a message that is now out of timestamp order, and at that point it detects a fault, and it knows that a fault condition has occurred, and now you need a fault handler to handle that situation. Okay, but you have this choice of either enforcing your availability requirements or enforcing your consistency requirements, irrespective of network behavior. So going back to the distributed database application, this is a program that actually implements precisely what I described, where you can have a global database where you timestamp events anywhere in the world, and they will be handled in timestamp order. And you'll have replicas of the data scattered around the world. And in this particular example, which you can download from the web, you can start up multiple windows to pretend you are a branch of the bank, and do deposits and withdrawals in these multiple windows. In the way in Lingua Franca, we timestamp events using the local clock is using a construct that we call a physical action, which gets rendered in the diagram as this little triangle with a P. But this produces an event that is timestamped by the local physical clock, and that will timestamp the time of the deposit or withdrawal. And then each deposit or withdrawal will be broadcast to all of the other replicas, okay? And each replica will respond to a user when it has collected all the information from the other replicas, if you use a strong consistency kind of design, okay? If you're emphasizing strong consistency, you use our centralized controller. Just a small point that our centralized controller does extend to some degree this distributed discrete event simulation technology because of this physical timestamping of asynchronous events. That was one thing that is not usually present in distributed simulation. And in addition, most distributed simulation frameworks don't allow zero delay loops like this. And we need them for strong consistency. So we had to do some extensions to support these, but that's a whole different talk. So I'll skip over the details of that. In this case, though, the Cal theorem tells us that if we have a design that emphasizes strong consistency, the price will be unavailability, and we can derive the amount of unavailability, which in this case will be the amount of time that it takes to respond to a user as a function of the network latencies and clock synchronization errors and so forth. And I want to point out again, network latency always gets added to clock synchronization error. We can't measure those two quantities independently, but we can measure the same through this apparent latency scheme. And apparent latency is actually what you really care about in this case. because the apparent latency is the difference between the timestamping of the query using a local clock and the response, the time at which the response is handled, which happens to again be using the same local physical clock. So this is simply the amount of time that it takes for the bank to respond to a user query. Okay, very natural measure of availability. And you can derive this using the Cal theorem based on the structure of the program. If the network becomes partitioned, the unavailability becomes unbounded with this centralized controller, meaning that the program blocks forever. And we would expect this from the CAP theorem. If you use decentralized coordination, however, the behavior ends up different. And this is what Google Spanner does. They use a decentralized controller in their distributed database system. And as a consequence, their database always responds to queries, even if the network breaks completely. Okay? If you have access to a local copy of the database, you'll get a response. Okay? They overlay on top of this a fault handling mechanism that is based on transactions, where anytime a record gets changed, a transaction schema is overlaid on top of it, and a transaction may get rejected if the network really does break. Okay, but that's a fault handling scheme. So I'll skip the details of that again. In summary, the CAP theorem tells us that network partitioning means you have to sacrifice one of consistency or availability. You have no choice. The Cal theorem quantifies this. As network latency increases, either inconsistency or unavailability must increase. Centralized coordination preserves consistency for all network latencies at the cost of unavailability. Decentralized coordination preserves availability at all network latencies at the cost of consistency. Fault handling. In both cases, the loss of availability or consistency beyond the program specification are detectable in Lingua Franca, and you can provide fault handlers for this. There's a much shorter summary. Certainty takes time. Okay, I think of certainty as consistency and taking time as availability. And I have come to see this as almost like a Heisenberg uncertainty principle of distributed computing. The more sure you need to be, the longer it's going to take you. Okay, if you're willing to be less sure, you can be quicker. Okay, but there's a fundamental trade-off there. So these are the references, and I'll stop there and take any questions or comments. Thank you.